Alaina wants to get the bus stop as quickly as possible. The bus stop is a grassy park 2,000 feet west and 600 feet north of her starting position. Alaina can walk west along the edge of the park on the sidewalk at a speed of 6 feet per second. She can also travel through the grass in the park, but only at a rate of 4 feet per second. What path get her to the bus stop the fastest? So this is an optimization problem. There are 4 steps we need to take. The first step is what we want. So here we want the shortest path. The shortest path means the shortest time that Alaina traveled from her starting position to the bus stop. Now for 2, we're gonna sketch this problem. So we start with Alaina, and then I'm gonna draw the sidewalk of 2,600 feet, and then I'm gonna draw the park. So again, this distance is the bottom distance is the west distance, so that's gonna be 2,000 feet, and then the north distance gonna be 600 feet. And notice our destination is to the bus stop, and across, if she wants to move across the park, then she gonna take X distance and then travel through the park. So here we have a combination of these. She can travel through the sidewalk, she can just take the grass, or can take a combination. So to solve this problem, we assume a combination of these is the best, and we'll determine the X value, whether it's 0 or in the middle. That will take Alaina the shortest to get her to the bus stop. Notice this, the length of this can be written as square root of 600 squared plus x plus 2000 squared. And note we are giving the velocity of Alaina at the park and velocity of Alaina at the sidewalk. So now after we sketch the problem, what we're gonna do, we're gonna move to step number 3. Step number 3 is try to form a function of the problem and then identify our domain or interval. So again, Alaina will move x distance, and then after this x distance, she will change her direction, whether going north 600 feet or going through the grass. So the total time gonna be the time spent on the sidewalk plus the time spent on the park. And remember, time is distance over velocity. Now for the distance on the sidewalk, we assume that Alaina just walked x distance, and then the velocity of the sidewalk given as 6 feet per second, and then the distance on the grass we'll assume that is y, and then the velocity given on the park is 6 feet per second. Now we'll substitute for the value of y, which is the square root of 600 squared plus x plus 2000 all squared. Then over the velocity again, which is gonna be 6, gonna be 4. Now this is the total time that Alaina will take to travel from her starting position to the bus. Now what's the interval? Since our variable her x, we want to determine what's the interval of x. So again, we can assume x going from 0 to 2000, 0 meaning Alaina will just take the grassy park, 2000 means she will move through the sidewalk. Now for step number 4, we want to find global minimum. Why? Because we want the shortest time that takes Alaina from her starting position to the bus. Here, let's look to the graph of the function t, or t of x. So what we notice in here, when we graph this function, we notice at x approximated to be 1463, there's a critical point. And that critical point is local and global minimum of the function. And the value gonna be, which is the time, it's gonna be 4:45 seconds. Therefore, when x is approximate to be 1463, time gonna be 4:45 seconds. This is the distance that will take Alaina to travel through the sidewalk and then take the grassy park. That is the shortest distance for her, and that will take the least amount of time. Now we have this problem: find the rectangle to maximize the area with one corner on the function y equal to square root of x. So notice here we have this rectangle going from a to 9, and what corner at the graph of y equal to square root of x. So again, the first step is what we want. Here we want to maximize the area of the rectangle. So we want to find the value of a that maximizes this area. So we are looking to the global maximum since we want to maximize the area. The second step is to sketch the problem. Here we're already giving the sketch. This is the function y equal to square root of x. This is the rectangle inside of the graph. Here we can note distance as 9 minus a, and the distance vertical gonna be square root of a. And notice here a can move right to left inside this graph. So we have these rectangles. We want to find the rectangle with the maximum area. So if we assume r is the area of the rectangle, then r gonna be height multiplied the length of the rectangle. Here the height is square root of a length is 9 minus a. Here we want to determine what's the interval of a. A can be from 0 to 9, which is our endpoints in the graph. Now, step number 4 is find the value that gonna maximize the area. So now we have the function and we are giving the interval. We just follow the steps of finding global maximum. So here we're gonna take the derivative of the area r and we'll equal that to 0 and define to solve for critical points. So again, r is 9. I'm gonna distribute the square root to the inside, and then notice that the second term, a square root of a, can be written as a1 plus half, which gonna be a to the 3 plus 3 over 2. Now r can be written as 9a to the half. I change the square root to the power half, and then the second term gonna be a 3 over 2. We can take the derivative. So what gonna do, this is just using the power rule. And then I'm gonna write half and minus half in terms of the square root. Notice that this function is defined for all values of a that is in our interval. And remember, our interval is going from 0 to 9. So now we move to where the first derivative is equal to 0. Now we solve for a in this equation. I'm gonna move the second term to the other side. And again, I'm gonna multiply both sides by 2. And then I'm gonna move a to the other side by multiplying that. Here, on the left side, we have square root of a multiplied by square root of a. That is just a to the power half plus half, which is gonna be a. Now we have 9 minus 3a, then a gonna be equal to 9 over 3, which is just a equal to 3. Note, a is equal to 3 is in our interval from 0 to 9. Therefore, it's considered to be a critical point for the function r. Now, we can evaluate our critical point 3 and our endpoint 0 and 9 in the function, which is r of a. So I'm going to take this function, copy that to the bottom, and then I'm going to evaluate our points, the critical point and our endpoints. Now notice that of a is 0 and 9. These are also can be seen as 0 from the graph. So if you move a to the a equal to 0, we don't have any area. The same thing gonna happen when you move a to the 9. There's no area, therefore it's 0. So now we notice that we have a global maximum at a equal to 3, and the global value is gonna be 10.392. So I'm gonna take, remember, a is equal to 3, and the square root of a gonna just be square root of 3. So now if we draw that rectangle under our graph, note here we have the first point to be a, which is 3, and the second point gonna be 9, and the height gonna be equal to the square root of a, which is the square root of 3. Now, notice this length here, it's gonna be 9 minus 3, which is 6. So, the maximum area gonna be square root of 3 multiplied by 9, which is height multiplied by length.